Let's get started. It's almost at least 12:01 where I am at. But welcome to our October general meeting. This is actually a very special meeting, and we'll go a little bit more into that in our next slide, I believe. But as for our agenda, we'll do a brief welcome announcements, and then we have a guest speaker because this is our general meeting. There will be an opportunity to ask questions with a little bit of time for wrap up if you have any questions for us. But today we actually turned 3. We had our first meeting on October 18, 2021. Robin, I saw your post. Yes, I know a lot of us have been here since the beginning, if not maybe for more than a year or two. So thank you for sticking on. And I hope that you got something out of this community. Yeah. And I hope we keep continuing strong and building a community of natural hazard and disaster researchers across the US and beyond. We've definitely grown beyond. And now, after a million announcements, and I know that was a ton of links, so please do reach out if you missed any. I would like to introduce our speaker for today, Dr. Koorosh Lotfizadeh. I hope I said that correctly, who is a project scientist and NHERI Operations Director for the large high performance outdoor shake table, which is at the University of California, San Diego. Dr. Koorosh, his interests are quite broad. He likes to researches a range from concrete bridges to looking at new technologies, sensor technologies, software development, machine learning, which I know are a lot of our interests here in this group. And he started at the UC San Diego team in about 2019, but prior to academia worked in the nuclear energy industry. So I'm sure people might have questions about that. So I'm going to pass on the screen to you. And yeah, we very much look forward to your presentation.
Thank you very much, Harman. Thank you, everyone. Let me share my screen here, if I may. Can everyone see the screen?
Yes.
Oh, perfect. Okay, cool. Well, hello, everyone. Thank you for having me here. My name is Koorosh Lotfizadeh. I'm a project scientist and the operations manager over at the large high performance outdoor shake table in San Diego. It's an honor to be here. Thank you for having me. Thank you, Robin, Harman, the entire GSC, for all that you do. Today, I'm going to briefly go over the shake table facility, what we do here, the importance of it, just to give you an idea of the type of work we do, and hopefully, inspire some people to pursue this kind of work. The outline of what I'm going to discuss today, we're going to briefly go, as an overview of the Engelkirk Structural Engineering Center, the home to the shake table facility. I'll talk about the shake table itself in the original configuration, the upgrade that we did recently to bring it up to 6 degrees of freedom, give it its full potential. We're going to look at some of our instrumentation and our data acquisition system that we have available here to collect the important data that we want, and just maybe touch on some new research opportunities that are made possible by this facility. So who are we? The leadership team at the NHERI at UC San Diego Shake Table facility consists of a principal investigator, currently it's Professor Joel Conte, and 4 co-PIs and myself. In the coming weeks, we are going to have a little bit of a change coming up with the leadership. John McCartney is going to be the new PI, and Joel Conte is going to be a co-PI, but that hasn't happened yet. So for now, this is the current breakdown of the leadership team over at this facility. There's a lot of text here. I don't expect anyone to read it right now, but if you want to reference it later, it just kind of gives a little blurb about what each person is responsible for at the facility. So running and operating such a large scale experimental facility requires a lot of work, and it's too much for just one person to handle. So we kind of break it out in a work breakdown structure, and each co-PI has their own domain where they focus on. So you can read that at a later time. An overview of the Engelkirk Structural Engineering Center. So I mentioned that name. It's more than just the shake table. We have a large facility that's about 10 miles east of the main campus at UC San Diego. It's kind of a bummer because the main campus is right by the beach, but we're inland a little bit. But we have more than just the shake table. And just to give you an idea, the shake table is what you see here in this yellow color. platform, but the facility extends way beyond it, and it kind of continues on to this side. We have two large soil pits and a strong wall, if you will, a reaction wall, where we can attach actuators, embed specimens inside either the north or the south soil pit. And just for reference, down here on the screen is the north side, above the screen is the south side. So we can, attach actuators and do some testing, cyclic testing as needed in these soil pits for soil structure interaction. We have, of course, the shake table facility and another facility, our blast simulator or extreme event simulator facility. It's been offline for a little while. We're working actively to bring that back online and refurbish the equipment. What that facility is capable of doing is simulate blast events or impact loading without using explosives. So it uses some really high-speed actuators that can generate incredible forces at an impulse and retract, not have that follow through. So you simulate an actual explosion type of event. In addition to what you see here that I didn't even highlight, we have some geothermal work that we do with solar arrays in the back over here. And along the entire length at the back of our facility, we have a full-scale railroad where we can do non-destructive testing and damage detection on rails. So we do a lot of work, but this presentation primarily focuses on the shake table facility. The Engelkirk Center, our center, we are an accredited ISO 17025 testing laboratory. So all the data that we produce here is accepted, in more than 80 countries around the world with no questions asked, because all of our equipment, all of our sensors are fully calibrated and documented and traceable. So the data that we collect is, of course, vital. You don't run an experiment and not collect any data. That kind of is pointless. So it's a pretty important thing to have this type of accreditation. So the shake table itself, let's talk about this a little bit. We've been in business for about 20 years now. Brief history of the shake table. It was designed and built in 2001 through 2004. It was commissioned in 2004. It was originally funded by NSF under the George E. Brown Network for earthquake engineering simulation, the NEES program. And we got some additional funding from the Department of Defense to build this shake table. From 2004 to 2014, our operations and maintenance was funded through the NEES program. There were two chunks of 5 years, similar to NHERI. That evolved into the NHERI program in 2016. We were funded through the NHERI program through 2022. But somewhere along the line in 2018, we got funding from NSF and some additional funds from the university here to upgrade the shake table to 6 degrees of freedom. This gives us a lot more capabilities, and we'll talk about that in a little bit. We reopened the facility around April, I want to say, of 2022, and we've been back in business since then, and our operations and maintenance has been funded through the NSF NHERI program. So the original shake table that was built, 20 years ago, was a single degree of freedom shake table. We used to have an actuator on the west side and an actuator on the east side, and we could only shake in one direction. We call that single degree of freedom. The platen itself is rather large. It doesn't look huge on this picture here, but it's 12.2 meters by 7.6 meters, so 40 feet by 25 feet. And it's a pretty large, heavy steel platen. And we can build specimens on it and attach it to the shake table and run some tests. It was always designed to be a 6 degree of freedom shake table. Now, when I say 6 degrees of freedom, I mean you can move in the horizontal direction, you can move in the lateral direction, you can go up and down, so you got all your translational movements. And in addition to all that, you have your rotational degrees of freedom. So you have your rolling, your pitching, and your yaw motions as well. So with all those 6 degrees of freedom, you can move in any direction physically possible. Of course, within some limits, you can't just infinitely rotate. But here, again, I'm not going to bore you all with the details. You can reference this later if you'd like. But we have some performance characteristics of, the stroke and the accelerations and velocities, etc., of the original system. Now, this is all abstract, so let's take a look at a video. On the left side here, you're going to see this is when we were commissioning the shake table back in, I want to say 2003, early 2004, where we're just demonstrating that this system can push and pull the shake table with a sine wave. So just kind of like cycle it back and forth at its capacity, 1.8 meters per second. So that's pretty violent. But we rarely just do cycles. We want to play back an actual earthquake. So this is after the commissioning process was complete. This is an actual earthquake. Yeah, pretty standard. But you can see that we can only push and pull the shake table in one direction. At that point, we still had very good tracking performance. Uh, when you give it an input ground motion, you want to replicate an earthquake that has already happened, we usually have an acceleration time history. So here in this little graph here, you'll see an acceleration time history in units g over time in seconds. And if you zoom in, you can see that the target and our achieved was very, very, very close. So we were able to reproduce ground motions pretty accurately 20 years ago. You got your spectral accelerations and your displacements as well, and we were able to hit those targets with very high accuracy. This allowed us to complete over 30 major projects on the shake table, ranging all sorts of different buildings. So we had power transmission lines, we had reinforced concrete buildings, a parking structure, wind turbines, some geotechnical soil boxes, with embedded piles and sound walls and things, timber buildings, there's masonry buildings, all sorts of things, you name it. We've done some testing on this stuff. And it's been very helpful and useful for the entire natural hazards community because you do need experimental data to validate your models. And we'll talk about this in just a second too. So looking a little closer at some of the past work that we've done here, this is an example of a project that was conducted, I want to say in 2011 or 12 maybe. It was a 5-story building, and this was a major project with high importance for this community because it was performed with 2 different systems. There was a fixed base configuration, which is standard old building that's attached to the ground. And there was a base isolated version of this building. So we tested both phases to see the performance difference. Now, if you're not familiar with base isolation, it's basically a layer that you will put in between your structure and the ground that would separate the two and allow the ground to move at whatever frequency and acceleration that it is. And that doesn't necessarily fully translate to the structure itself. So we'll see coming up how that actually performed. This building was, we call it the BNCS program. It was a 3-phase project on the shake table. It was a total building system with cladding and the facades. On the top couple of floors, we had precast concrete cladding. On the lower floors, there were balloon frame metal studs with a stucco finish system. It was 5 stories tall. Each floor had a different occupancy type, so we wanted to see how these non-structural components would perform during an earthquake. Also very, very critical for our community. The bottom floor was modeled as a utility closet where we have utilities. There was a lab and a residential floor. There was a server room that later in one of the phases we actually set fire to. There was an ICU unit fully equipped with, hospital beds. There's a surgical suite with, equipment hanging from the ceiling. There was a full working elevator and a staircase inside this, and there were garage doors and different types of windows and doors throughout the building. So this was an all-encapsulating kind of project to see the performance of not only the structural components, but also these very, very critical non-structural elements inside a building. You wouldn't want to be getting operated on and there's an earthquake and suddenly the equipment just falls off. That doesn't sound very good. So this building, we'll watch a little video here of the performance. There's too much information here, so we're not going to talk too much about it. But this thing that you see here is a base isolator. This is basically a lead core with rubber on the outside. And on one end, it's attached to the ground, and the other, or the shake table in this case. And on the other, the building kind of sits on it and is attached to it. So you'll see as you're moving, the isolator kind of stretches and moves around, not translating all of the forces directly to the building. We have a little hysteresis plot here that can show the shear strain and the base shear on the building as well. A little in this video, we're going to see two comparisons. We're going to see a base isolated version and the fixed base version. So let's just take a look at this really quick. So you can see as we're moving here, that isolator is really stretching, dissipating energy as it goes. And here is the base isolated and a fixed base. And you can see the difference in performance when you have a base isolator or you don't. And important thing to note is this is 100% scale of an earthquake from Peru. The base isolated version was 140% scale. So even higher scale accelerations, and the performance was so much better inside the building, just to demonstrate how critical that type of isolation system is. Another important thing, and the reason I'm showing all of this, is the work we do is very important. There's some structural failures that are really difficult to capture in our computational models, to capture accurately in computational models. Some of them could be bond slip, there's rebar buckling and fracture, there's slab failures at the column joints, a whole host of failure mechanisms are really complicated to capture. So having these large-scale or full-scale experiments to see how these perform and collect data, we can validate our models, we can improve our models, and eventually progressively move away from experimental testing and relying on experimental testing and improve our models to a point where we can rely more and more on that. So we don't have to spend so much money and time on large experiments. This little video here, again, it's a short little clip. You'll see at the top, this is the slab, the floor, and a column on the third floor. You'll see the slab failure as this building is shaking. You'll see it start to pull and rotate, and that slab is failing at that connection. On right below it, on the second floor at the drop ceiling, this is a beam column connection. You'll see that as it's moving, there's some rebar at this joint here that fracture, they buckle and fracture, and you'll see some little concrete exploding out as those rebars start to fail. So all of these failure mechanisms are really difficult to capture accurately in a model if you don't have these kind of baseline test data. So here we go, let's take a look at this. Just you see that slab here kind of bending up. That's a pretty bad failure. And boom, we just saw that explosion here with some rebar. And that joint is just fully opening and closing at this point. So it's lost quite a bit of its integrity. This is a fixed base test, by the way, not one of the base isolated tests. Oh, I forgot to mention at the top, there was also a full chiller system where you saw some water falling out as we were shaking it. So that was kind of cool. So not only, I did mention earlier that we did some geotechnical experiments as well. So we can look at, investigate a lot of soil structure interaction type of performance for structural systems using two large soil boxes that we have available at our facility. One of them is a laminar soil shear box that has multiple layers with rollers in between so they can move relative to one another. And one of them is a large stiff confinement box that you can embed specimens into, create retaining walls and things of that kind of nature. So using these boxes on the shake table, we can validate, of course, our computational models will complement the centrifuge tests because those are often on really smaller scale. So we can complement all the centrifuge tests, we'll validate our computational models that way. We can study the performance of bridge abutments, retaining walls, slope stability, and hillside construction, underground structures. So if you have like a tunnel that you want to embed under the soil, we can do that kind of work. And of course, we can check liquefaction using the laminar soil box as well. And if you're not familiar with liquefaction, it's when you saturate soil and as it shakes, it tends to kind of liquefy at the top. And that causes massive problems for structures that are built on top. Just another quick demonstration of one of the past experiments that we did here at the shake table, all during the earlier phase in the single degree of freedom. This was a project that utilized the laminar soil box installed on a wedge to simulate a slope. And this picture that you see here is after the test is already completed, but you can see how it deformed and each layer of that soil had moved independently or relative to one another. Inside this box, they had a pile that was embedded, and I'll show you the video on the next slide of just how critical it is to have this type of box to do this testing. So we're going to take a look at this video. Just pay attention here. You'll see this pile, as you're shaking, it start to walk. It starts to move. And you can imagine if you're supporting a structure on top of that pile and that pile starts to move, that's probably not good. So here you'll see this thing shaking, and then paying attention on the right side, you'll start to see it open up and the pile starts to walk. So that becomes a little scary. So we have this frame here to support, these layers so they don't just roll right off, because we knew it would. And at the end of the test, you can see that they were pretty much touching that frame. Okay, so all of that was the single degree of freedom shake table. So we did all that critical work in just one direction of shaking. When we upgraded this system to 6 degrees of freedom, this opens up a whole new world of possibilities for us. The upgrade, just to show you what it looks like now, in the earlier slide, we had a little picture of the single degree where we had one actuator mounted on this end and one actuator on this end. This is just a little rendering, a little slice so you can see the insides. Now we have 2 actuators on either side positioned in a V shape, and we have 6 vertical actuators underneath the shake table for the upward motion. So you'll see 3 of them on the north side that we're looking at right now, and then there's 3 mirrored on the south side. All of this is powered by a massive hydraulic system. Well, this all had to be redone for this upgrade because we now needed a lot more hydraulic fluid, a lot higher velocities, a lot higher flow, a lot of pressure. So just to give you a brief overview of this, some of you have maybe been on a tour here at the facility. Those that aren't familiar, I'll spend a minute just looking at this. We have a large surge tank here that stores, about 5,000 gallons of our hydraulic fluid. We have a bunch of pumps, and we have 4, I call them a bunch, but these pumps take that oil and pressurize an accumulation system that stores this high pressure fluid. And when we need it, we got these blowdown manifolds down here that release that high pressure oil through the red pipe going under the shake table. So this is all under the shake table. What you saw, the vertical actuators are right here. And then you can't see in this picture, but there's some horizontal actuators on that end. So all that hydraulic fluid, that high pressure fluid comes through, creates a little ring around and feeds oil to each one of these actuators. And that's how they move. When that energy is spent, that low pressure oil returns through the blue pipes and goes back into that tank, and that whole cycle repeats as we need it to. All of this had to be redone. These pipes, everything had to be reworked and enhanced in size for this upgrade project. Now, I did mention the accumulator banks here. We can't run with direct pump. We need some sort of accumulation. If we were to use just pump power, we would need 100 of these pumps, or I don't know how many, to generate enough flow for the actuators to move as we want them to. So in order to avoid that, we use an accumulation system. The accumulation system consists of 75 large bottles that are about 130 gallon capacity each. And inside each bottle, there's a piston. And on one side of the piston, we store 3,000 PSI nitrogen. And those pumps pump oil to the other side of the piston, increasing that pressure to 5,000 PSI. And once the pressure inside each one of these bottles reaches 5,000 PSI, we close off the valves. We store that high pressure oil inside. And as we need that oil, we blow it down through those red pipes that we saw earlier to the actuators. All of this is really critical, and we need to keep an eye on the pressure inside each one of these bottles, the temperature, some metrics, because we need to make sure everything's operating properly. We have some analog gauges. You kind of can see them in the picture. Each one of these bottles has a gauge on it that shows you the pressure. But when the system is on, it's too dangerous to be in this room. So these analog gauges really aren't very useful. So to bypass that, we have these wireless sensors. You'll see all of them at the top here that collect this critical information, pass it on to our gateway, and I have my own server and database that I store all this in. And we create little dashboards to visualize and trend the pressure and the temperature and all that. So just to show you what I see, we can see the pressure over time. And these fluctuations that you see, it's kind of interesting that as the temperature fluctuates throughout the day, you naturally get pressure variations. And this is all important. And previously, we weren't able to see all this because you only have an analog gauge, so you only get a little snapshot in time. But we can actually see the current pressure in each one of the models in real time as we're operating the table. So it's kind of a big deal. Once again, performance characteristics. This is now a 6-degree freedom table. I don't expect anyone to read all this. I'm not going to bore you with it. You can reference it later if you're interested. We still have, of course, the same platen, the same 40-foot by 25-foot platen. Our frequency bandwidth hasn't changed. Our vertical payload capacity now, since we can move vertical, is very large. It's actually the largest in the world. It's 20 meganewtons, so 4.5-ish million pounds. If you ever do reference this table later on, just keep in mind that it's split into 2 sections. There's the bare table condition, and then there's the condition where we assume a centered rigid payload of 4.9 meganewtons or 1.1 million pounds. So the characteristics are a little different depending on what you have on the shake table. Again, we're just going to blow right past it. But looking back at the tracking performance, like we saw in the single degree of freedom, we've demonstrated through our commissioning that we are still reproducing these earthquakes with really, really high accuracy. This is just a demonstration of the Kobe earthquake in 1995, or yeah, I think it was 95. And you can see the X direction, Y direction, and Z direction, acceleration, velocity, and displacement. One thing I didn't mention is the shake table is a 3-variable control. So we can control it using acceleration or velocity or displacement. We can choose what we want to control it as. We typically, for earthquakes, control with acceleration because that's the ground motion that we generally care. So let's take a look at some shake table movements just so you can get an idea of what it looks like when it moves. This is when we were going through our commissioning, so all these protective covers are not installed, so we can actually see what's going on. What we're about to look at is an AC 156 compatible earthquake, usually used for seismic qualification of equipment. This is in 3 degrees, so it's XYZ, but there's no rotations involved in this. But it'll give you a little sense of just how violent and impressive it can be. I don't know if the video is coming through okay or not. Sometimes Zoom isn't really friendly. I wouldn't want to be on that. Yeah. A Tabas earthquake in Iran, 1978. This was a magnitude 7.4 earthquake. Also, it's an XYZ, so all 3 translational degrees of freedom. And lastly here, we wanted to demonstrate the rotational degrees of freedom. So we couldn't find any ground motions that had, all 6 degrees of freedom. So we made a synthetic one just to demonstrate what it looks like when we actually rotate this. And I actually really enjoy this video because it looks like kind of like the ocean. It's very fluid as it moves. We do have limitations on how much we can rotate. And if you look back at the characteristics that I showed on the screen, it's only a couple degrees. You see it says, oh, rotation about the y-axis is only 2 degrees. When you actually put it in perspective, that's massive considering the size of this thing. So rotating 1 degree or 2 degrees over 40 feet is a rather large rotation. That was just to show how the system looks. So we did all this. We upgraded the shake table, and we reopened in 2022, and we immediately went on to testing the tallest building ever tested on a shake table. It was a 10-story mass timber building, collaboration with several universities. The PI was Professor Shilling Pei. over at Colorado School of Mines. This building was fascinating in many ways. There was 10 stories, mass timber, proof of concept type of building to allow mass timber structures in seismic regions to exceed a certain height limit because our code currently limits that. There were several interesting mechanisms here. I'm not going to go too in depth with the details, but on the lower 3 floors, on all 4 sides of the building, there were different types of facades. So they were investigating different type of facade, cladding, windows, doors, etc. But the coolest thing about this was the lateral force resistance system. These large walls that you see go up all along the height of the building, they were rocking walls. So at the base, they're not fixed to the ground. During motion, they were able to rock back and forth. And along the height of these walls, you'll see, maybe you can see there's little cutouts on the sides. There were little energy dissipation, U-shaped steel plates that as that wall would rock back and forth, they would dissipate energy through yielding. So along the height, you would have energy dissipation. There was some post-tensioning that went all the way down for the recentering force to bring that wall back to plumb after the event. So that was really cool. Just take a look at a couple of videos here, or one video, an overall view of the Loma Prieta earthquake, MCE level. Just for those that aren't aware, MCE level earthquake is an earthquake that has a mean return period of almost 2,500 years. So it's a very rare earthquake, and it's rather large in magnitude and can be catastrophic. So this is one that happened in Loma Prieta in 1989. You'll see inside the building where there was the staircase, there's a column, and this one is just to show you how these columns had an interesting two-way pin mechanism at the base to allow rotations while still being able to carry the load. And the corner of one of these rocking walls, so that's at the base of one of these walls here. You'll see it as we're shaking it, you'll see this base just kind of lift up, open and close during the motion. Ooh, sorry, that was louder than I thought it would be. So yeah, that was a very interesting project. Now we finished that guy, we did some other work, and now we're finally embarking on our next project, which is another 10-story building that we just broke ground on Monday. This one is going to be cold form steel. It's colloquially known as CFS10 because it's a 10-story building. It's a little bit shorter than the mass timber building. That one was about 120 feet tall. This is 100 feet tall. So it's not going to break that record, but it's still an impressive feat. This is a full-scale slice of an archetype building that's designed in common cold form steel standards of today. So obviously you can't fit the entire building on the shake table. So, this one is going to be a slice of that building. And there's some interesting things that this project is going to focus on. So currently, we're also height limited for cold form steel buildings. ASC 7, the design code, says to go less than 65 feet in height, and this one's going to push that to 100 feet. So that's going to be one of the main things to look at. In this project, this one's also got a full facade and doors and windows and non-structural elements inside. And there's 2 phases to this project. This one's going to have an earthquake phase where we do our earthquake shaking. And after that, there's going to be a multi-hazard investigation. So we want to know what happens in case there's a fire after an earthquake. So once we've done all the earthquake testing, 4 of these floors are going to get set on fire. I think they're going to be set on fire independently. So like 1 floor, etc. And we're going to see the performance, and the strength degradation of the structural components and non-structural components in the event that there's a fire after an earthquake. So this is going to be a very interesting project that's happening now at the Shake Table. All right, bored you enough with that. Let's switch gears here and look at some instrumentation and data acquisition, and I promise I'll keep it as short as I can. I mentioned earlier, instrumentation, data acquisition are very critical for everything we do here. Without it, all these tests are kind of pointless. So we need to be able to collect the data, collect it properly, and then store it securely. Our data acquisition system, yeah, I'm not going to explain all this stuff, is a state-of-the-art 24-bit system. We purchased it through National Instruments and components and built the entire thing ourselves. We have 13 what we call nodes. So each system, we consider that to be a node. Each node is capable of recording 64 channels. So 64 sensors can connect to it and we can acquire data. It's 24-bit ADC resolution. They're capable of 25,000 samples per second, simultaneous sampling. And it's very scalable. So the way we currently have this set up is we have it in 3 stacks, A, B, and C. And each stack has several nodes inside it. And they're all interconnected, so they're fully synchronized with each other. Now, the Shake Table controller has a trigger output that we feed to each one of these 3 stacks to make sure that when we run an earthquake, we're recording the data simultaneously with the Shake Table. So you can cross-reference and check the data that you got from your sensors with the movement of the Shake Table and make sure that they're all in sync with each other. In addition to the data acquisition, the Shake Table control outputs another trigger line to our video recording system where we have a whole bunch of cameras that record video. So all of our Shake Table movement data, the instrumentation and data acquisition data, and our video and picture data are all fully synchronized. And they're all connected on a local network, and we have a local dedicated PC that operates these systems. Our main objective, of course, is to provide quality data and make sure our equipment is in tip-top shape and everything is traceable. So to do that, we need to maintain calibrations. We have to have proper documentation and all that. So we have many equipment available to perform standard calibrations on all of our equipment, and we do this every year or every 2 years as needed per device to make sure everything is properly maintained. So some of the instrumentation that we have available, we typically use a lot of accelerometers, linear displacement transducers, inclinometers. There's some load cells and things. Primarily what people tend to use on research when you're dealing with Shake Table stuff or seismic work is accelerometers and displacement transducers. Now, whether they be linear displacement transducers like what you see in this picture, or the string potentiometer displacement transducers like you see down here, they all just measure displacements. And accelerometers obviously measure accelerations. In addition to that, when you're dealing with these tall buildings, you can't really measure the displacement at the top of a 10-story building because you don't have a reference column that tall to measure off of. So for those types of tests, we have a GNSS system with 10 receivers that operate at 100 hertz. So we can collect reliable displacement data at heights that you just don't have any reference for. And of course, I mentioned earlier, we have a bunch of cameras and drones that we also use with all of the tests that we do here. So just keep this really short, one slide on some new research opportunities, and we can chat if you have any questions. This 6 degree of freedom Shake Table does open up a whole new world for us. There's a number of research topics that we need to answer, and there's plenty of questions that we have in this community. We have a publication that we from a few years ago that has a bunch of this information in it. There's a lot of interesting questions that have been posed and ideas that have been thrown out. But just one that I wanted to highlight here is this 6 degree of freedom capability. Up until now, we haven't been collecting rotational information from earthquakes just because for 2 main reasons. One being seismologists, they didn't think it was that big of a deal. They're like, the rotations, aren't that big of a deal. they're not going to affect anything as much. They're small rotations in the Earth. So they're like, we don't need to worry about it. And two, it's actually quite difficult to collect rotational information from earthquakes. So we haven't had that up until now. But recently, this Trifunak in 2009 demonstrated uh, that the ground, as it rotates and as you have some horizontal translation, it can really impact the overall drift of your building. So if you're moving, your ground is moving horizontally and it's rotating, the top of the building, especially if it's a tall structure, that drift amount is enhanced significantly. So even if you have a very small rotation on the Earth, it can have really dramatic consequences on a building. So as this knowledge is becoming more and more prevalent in our community, the need for a 6 degree of freedom shake table is becoming more clear. So that is one of the things that we can investigate, aside from a whole bunch of other things with soil structure interactions, liquefaction, things like that under rotational motion or in 3D motion. These are all critical things that we need to look at. And with that, I know I'm a little over time. I apologize. I'm just going to end it here and we can chat and ask questions or discuss things as needed. Thank you.
Thank you so much for your presentation. Yeah, this is open question time. So if you have any questions, feel free to unmute, put them in chat. Yeah. I think while everyone is thinking, I definitely had a question, is do you collaborate with any other NHERI sites? Can you talk about more interdisciplinary projects?
It's a little challenging. That's we want to. It's a little difficult to collaborate and from our perspective because the type of work we do, it's very kind of niche, if you will. But our collaboration, we've collaborated with the Rapid facility on imaging techniques in the past, I know. And we work with the UC Davis, the crew over at UC Davis, the centrifuge facility, quite a bit as to get best practices and things. It's not so much for the work itself, because it's a little different. But with the Rapid, we do with reconnaissance work and imaging or drone work and things, definitely. And of course, I need to mention SimCenter. Their tools are incredibly valuable, and we work with them quite a bit too.
I see Anamika, you have a question. Go for it.
Yes. So I was thinking, well, you mentioned why, like, we used to ignore small rotational values already, and you said they've been like quite important. So, what kind of do you think they were always important, and we didn't have tools to record them? And now that you read it, what kind of value, like, how much does it affect, like the magnitude or the effector? Or which part does it beam? What structural component does it affect the small rotations?
Oh, that's a great question. Yeah, of course, there have been rotations always, right? It's not like they suddenly started rotating. The importance of it just wasn't known. And I did kind of briefly hint that our computational models can now be improved because we have this kind of test capability. So the rotations have been kind of ignored for a while because they are small, but their impact could be significant and it could not be significant. In particular, when you're looking at taller structures, that tends to be more noticeable. Of course, it's not limited to that, but now that we have this ability to actually collect experimental data, we can improve our models to account for whatever effect it would have. It's hard to quantify what effect it would have on a structure because it could vary, from one to another. I don't know if I'm completely missing the answer to your question here, but I can't just say, yeah, it's going to be 10% or 20%. It's not so easy to quantify that.
Also, one more question, just adding to this, because now we have so much experimental data, and we are, you said it'll improve our numerical simulations. So, what do you like? What degree of like the data you collect from the systems, like to which order of high statistics do you make sure that is correct? So that, and how are we improving models? Because I think we're already third, fourth order of statistics we do that. So, are you pushing beyond that in the collecting so that we get more and more accurate data? Is that also a part of it?
Definitely. So that's, of course, that's always a part of it, right? To improve the accuracy.
Mm,
But there's another side of it that I'm personally more focused on, and that is the behavior of components. So I mentioned,
yes,
and I showed a little video of the BNCS building where we had
yes,
the slab failure, right? So to
yes,
be able to accurately capture that, rather than, rather than looking at the response of something that's known and try to make that a more accurate response, I'm
yes,
more focused on the unknown, the things that we haven't been able to capture numerically,
yes,
um, or predict numerically.
yes,
So this experimental data, one of the major important things from my perspective that we get out of it is that we can see that, oh, there is this mechanism that previously we hadn't built into our models. We didn't know
yes,
that this could happen or how we can capture that. Through my own research several years ago, I did a whole study on bond slip, for example. And through my experimental work, I was able to capture some behavior that there was no models for. Like I'm like, oh, cool,
yes,
it's pretty neat. So
yes,
it's not just improving the accuracy of the known parts. I
yes,
think it's more about improving our models to capture things that we haven't been capturing.
yeah. That is actually, yeah, very significant. Thank you.
Of course, thank you.
Do we have any other questions? Yes, Esteban, go for it.
Yeah, thanks for the presentation. Who can do research on the shake table and how does that usually work? Can you explain the process?
It's a great question. We are a national shared use facility, and we're funded through NSF, the NHERI program. Anyone can use our facility. Now, it's not as easy as, hey, come on in, let's just do it. Generally speaking, shake table experiments, they cost a lot of money. They require a lot of time, a lot of effort. And depending on what it is that you're testing, it could be a massive 10-story building that's going to require, years of prep work, millions of dollars, or it could be a component that you want to test out and use it as a payload on an existing project. So there's a few different avenues we can go, but the general concept is you write a proposal if you want to be funded through NSF. Write a proposal, meet with us at the facility, myself primarily, or any one of the co-PIs of this facility. And kind of discuss with us what you want to do. We can help you prepare, your proposal or your budget or whatnot. So you write this proposal. Let's say you get funded. You get on the calendar for the shake table, the schedule here. You get in line, and then we help you build it and test it, hand off the data to you. If you're not going the NSF route and you just want to privately fund it, you just contact us, tell us you want to do this, have your funding squared away, and we'll put you on the schedule and we'll do that. It tends to be a lot more expensive if NSF isn't subsidizing it. So I don't recommend that, but that is an option. Now, the other thing that I mentioned with the whole payload concept is, let's say you just want to look at a damper mechanism or an energy dissipator or some new door or window or whatever that you're designing. And you don't want to build an entire building to do it. You don't want to spend millions of dollars and write this massive proposal trying to get funding to build a building to test your little component. So what you have an option to do is a payload project where it's far simpler to get approved and get some funding to do a payload. You say there's currently going to be a 10-story building on the shake table, and I just have this energy dissipator that I want to test out. I can install it on one of the floors of this building. So you piggyback off of an existing project on the shake table and install your component, test it, get your data, and move on. So there's several ways of going about this. If you are interested in pursuing a project here, which I highly recommend you do, I suggest getting in touch with me or anyone. My contact info is on the screen. And we can work through it together and we'll help you. It's a complicated sounding process, but once you start talking through it, you'll realize it's not that bad. So we're here to help.
And thank you. And for the sake of time, can I ask you to answer one question in 30 seconds? And it's in chat. Is the placement of the sensors to collect, what I guess the question is about the placement of the sensors. Is it in the entire base or is it in the floor boundaries?
The sensors that are installed on the specimen?
To,
The collect rotatable.
yeah.
Here, sorry, I'm going to stop sharing my screen so I can actually see the
Go
chat
for it.
question. I apologize.
Poria, it's okay if you just tell them what your question is. It might be easier.
Yeah.
Hello.
Hello.
So is it kind of load cell then capture all it's not load cell, but to capture displacements or something, or you're recording the rotational displacements in the floor boundaries?
For rotational motion in particular, in the
Yeah.
building, we primarily use inclinometers. So it's a sensor that just measures rotations. And you can install them strategically. You only need to put them in 3 points to get the rotation of a plane. So if you're a little strategic, you don't need to instrument too much to get rotations. If you're looking at local rotations, of course, you increase your instrumentation in a local region to catch different types of rotation. The shake table itself, I'm sorry, this was supposed to be 30 seconds. Shake table itself measures rotations using kinematics of the 6 vertical actuator displacements, because that is what generates the rotation. So we know the base rotation, and then on each floor or as your specimen height increases, you can instrument it with inclinometers and displacement transducers, depending on your setup.
Gotcha. Thank you.
Of course.
Yeah, if anyone else has more questions, please do connect with Dr. Koorosh on LinkedIn. His email is in chat. And I quickly also want to share about our next meeting. And again, thank you, Dr. Koorosh, for coming to our meeting. This is great. Our next meeting is on November 15th. We actually do have a confirmed speaker. It's Dr. Joanne Browning. So looking forward to that, and we'll send out more information closer to that meeting. But thank you all for coming today. And that's all we have. But please do get in touch if you have any questions for us or Dr. Koorosh.
Thank you for having me.